Thank you so much, Mr. Chairman, for this kind introduction. I would like to begin by thanking also to the organizers of the conference for giving me this very nice opportunity to give this talk. But even more importantly, I would like to acknowledge the people who did most of the tough work included in this presentation. David González and Iciar Alfaro, associate professors in the University of Zaragoza, Carlos Quesada, actually doing his PhD thesis with us, one of the pillars of the team, Professor Francisco Chinesta, and also Antonio Huerta and Pedro Díez from the Polytechnic University of Catalonia, who participate in a coordinate project whose result I'm going to present today. Well, my intention is to speak today about, if not a new science, a new discipline, which is that of computational surgery. As you can notice, an operating room is now becoming more a computer cluster than a traditional operating room. So computers are increasingly playing a very important role in the development of surgery, both for planning during the surgery, for surgery outcome prediction, and also, and very importantly, in training surgeons. So, in words of Marc Garbey, who is the editor of the Journal of Computational Surgery, who is now in its first volume, computational surgery is the application of mathematics and algorithm design, enabling imaging, robotics, informatics, and simulation technologies, and incorporation biological and physical principles to improve surgery in any way. Well, the prediction of surgery outcome is a very tricky task. From the early days of now called video surgery, endoscopic surgery, it has been clear that surgeons need for a very specialized, very specific training in the field. Okay, so one of the very important aspects of this kind of techniques is the need for a risk-free training of surgeons. Okay, so why not thinking of computational simulators as a way to train surgeons? But this faces important challenges. The most important challenge is the real-time simulation of the very complex coupled and nonlinear phenomena occurring during surgery. We will be dealing with strongly nonlinear solids. Soft living tissues are usually modeled as hyperelastics. We will need to take into account solid dynamics, contact, cutting, suturing, many challenging phenomena. In this presentation today, I'm going to focus in one particular aspect of computational surgery, which is the development of a surgery simulator. Okay? Here you see the Da Vinci robot. It's a robot to practice surgery. You see here the surgeon far away of the patient. Okay? He's manipulating joysticks, and there is a challenge in the sense that he is not feeling any force, any response of the body of the patient. So they risk to produce very important damage in the patient. Okay? They need for a very specific training. Well, other training devices, you can find here two specific examples for knee and shoulder surgery, incorporate this type of apparatus. This is a haptic device, okay? An apparatus that provides you with the sensation of touch, the sensation, the force response of the system. In a sense, a surgical simulator could be sketched in that way. You manipulate a haptic device. The haptic device determines the position of the surgery tool in the virtual space. It detects contact with the organs, with the tissues, It computes the deformation field by applying appropriate constitutive equation. It computes the stress fields, and by integrating the resulting forces that are transmitted to the haptic peripheral. But in order to provide a realistic sensation, very much like you need some 25 to 50 frames per second in cinemas to perceive a continuous motion, you need some 500 to 1 kilohertz response in force feedback. Okay? Well, of course, you can imagine that this is a challenge. You need to simulate and to show your resulting images at 20 Hertz. Contact detection can be made in a parallel thread in the simulation at about 200 Hertz. But more importantly, you need to simulate the deformation of strongly nonlinear soft tissues at 1 kilohertz. 1,000 times per second. Any of you that have played with Abacus know how much time a hyperelastic simulation takes in an average computer. So the challenge of doing this 1,000 times per second is clear. Well, this is more or less a disclaimer. Okay, here in the audience, we are all familiar with scientific computation. In scientific computation, we are familiar with very accurate results, and we don't care so much if this simulation takes time, in the order of hours. Why not? One night is the limit in the industry nowadays. But if we consider surgery planning, we should consider minutes in order to provide an useful result. And in the limit, if we consider haptic rendering, provided the 1 millisecond constraint in the result, we are able to accept an important loss in accuracy. The purpose of this research project is to improve the accuracy while maintaining the speed of the simulation. Well, if we take a look on the state of the art in the discipline, Professor Satava made a taxonomy of the existing surgery simulators. He distinguished a first generation of simulators in which only the anatomy is represented accurately. Okay, the shape, morphology, essentially the surface of the organ is represented accurately. We can consider a second generation of simulators in which the physics of the surgery is considered accurately. The deformation, forces, temperature, why not? And we could say that this second generation of surgical simulators has not been completely fulfilled at this time. There is a consensus among the surgeons that existing simulators do not provide a realistic sensation. And this is mainly because the deformation fields, the resulting stresses, etc., are not realistic, are not accurately simulated. We can think of even a third generation in which cells, the activity of the brain, breathing, bleeding, etc., are considered, but up to my knowledge, there is no such simulator today. Satava distinguished up to 5 generations, finally at a genetic level, but this is nowadays out of reach completely. Well, taking a look at the history on the development of such simulators, the history began by using spring mass systems. These are very convenient, very simple models. Cutting is very easy to simulate. You just remove a spring and you have a cut, but the result is very poor. You don't even represent the laws of linear elasticity. Fast finite elements represented a step forward in that sense. The inclusion of linear elastic homogeneous response of the organs by means of static condensation and storing in memory as much information as you can, storing in memory the inverse of the stiffness matrix of the system. Okay, and this is a key point in the history of such systems. So far, biquadratic springs that reproduce hyperelasticity have been developed, and nowadays the state-of-the-art, more or less, include the so-called total Lagrangian explicit dynamics by Professor Carol Miller, and of course the intensive use of parallelization on GPUs, etc. Well, as I mentioned before, we consider this as a key idea in the development of surgical simulators. Is it possible to store in memory as much information as you can? In other words, is it possible to pre-compute everything and just store in memory and show the results, not simulating in real time, just post-processing in real time? Of course, if you are dealing with nonlinear tissues, dynamics, etc., your response maybe will be no. And I will try to convince you that if not all, many things can be pre-computed and stored in memory in your computer. Okay, that's the origin of the concept of computational vademecum that we developed some years ago. There is a strong tradition in the field of engineering of developing books that contain known solutions for engineering problems of interest. This is the Bernoulli vademecum of mechanics. Okay, it contained a lot of solutions for known problems at the time. But we can think of updating the concept of vademecum today. You can embed real-time simulations on an e-book, for instance, on a tablet or a smartphone, and play the same role. Okay, it can provide you the solution for a engineering problem of interest. But this kind of vademecums can be consulted not only by engineers in practice, also by computers. Well, that's the idea. Why, instead of pre-computing the displacement field of a cantilever beam, for instance, you can't imagine the solution in real time of a cantilever beam by real-time simulation? The problem is that once you augment the number of parameters in your simulation, you consider problems in a parametric way. You consider, for instance, typically the displacement field in your organ, depending on the physical coordinates, time, the position of the loads, any other parameter you can imagine. The space where this solution lives is R to the power of the number of parameters, okay? But the number of degrees of freedom of the finite element mesh of such a domain increases exponentially with the number of parameters. That's a challenge that has been coined as the curse of dimensionality. In words of Professor Loughlin, a Nobel Prize laureate, no computer existing or that will ever exist can break this barrier because it is a catastrophe of dimension. Okay? But it is clear that some kind of model reduction is mandatory if you are trying to solve this kind of parametric problems, or in other words, a vademecum. If we think of classical model reduction, the so-called proper orthogonal decomposition, the idea is to decompose your solution U by an approximation, say up to m terms, in which the solution is composed by space and time functions. And these space and time functions are determined by pre-computing the so-called snapshots, solutions to full problems solved in a standard way. Okay? So here U represents the solution of a full problem, and by minimizing this norm here, you determine the best space and time functions that best approximate your solution, in the hope that these functions will be also optimal for problems in which you change slightly the parameters. The problem here is when you face nonlinear problems. In that case, you have the tangent stiffness matrix times your displacement vector equals the external applied force. You project these equations into the basis functions phi by pre and post multiplying the stiffness matrix. And the problem is that every time you need to update the tangent stiffness matrix, you need to reconstruct the full problem. And this is a loss of time. Also, the interpolation of reduced models computed for different values of the parameters is still a challenge. Well, in this sense, we have preferred to employ a different method. This method is known as the proper generalized decomposition. The proper generalized decomposition generalized, and that's why the name, the previous approach, in the sense that these functions can be not only space and time functions, but can only include an arbitrary number of parameters. But there is a second fundamental difference, is that functions are a priori unknown, are computed on the fly by the method instead of solving complete problems from which to extract the functions. These functions are computed by means of greedy algorithms, in the sense that we compute one sum at a time. Each sum is composed by several products, so we face a nonlinear problem. But every function is computed by using your favorite linearization technique. In our case, we employ fixed point iterations that work very well. Okay? These functions are then obtained by minimizing the residual. Well, let's try to see what happens if we apply PGD to the computation of computational vademecums. The idea is to develop a sort of general parametric solution, in this case, say, the lever, for instance. Let's consider, to begin with, the case in which the parameter is the position of the load. We would like to obtain a solution, a general solution for the displacement of the lever for any physical point x, for any possible position of the load, the position of the surgery tool, and for any value of this load. Okay? As you can see, this is a problem defined initially in a space of 8 dimensions. Well, the idea is the following. Consider the wake form of the problem, the standard one, but one slight difference. We are integrating, this is a doubly wake form in which we integrate in the area where the load can be applied by the surgeon. This is gamma hat, okay? We regularize the load term, which is a delta function here, and we assume that the solution of this parametric problem, of this vademecum, will be expressed in a separated form as a product of functions depending on the physical coordinate x and functions depending on the position of the load, what we call S. Imagine now that we would like to enrich this solution. We would like to compute a pair of new functions R and S. We compute an admissible variation of this solution and inject that in the wake form of the problem. Okay? If the problem is nonlinear, as is the case, you don't have time to update the tangent stiffness matrix. So that's why we have decided to employ a very elegant solution developed by Professor Michel Poitier-Ferry, which is called the asymptotic numerical method. We expand the displacement, the second PO, a Kirchhoff stress tensor, and lambda, a load parameter, in terms of powers of A, which plays the role of an arc length parameter. Okay, and we inject this expansion into the waveform of the problem, given a very nice sequence of problems, one for each order of the expansion, from order 1 to order P. Once you discretize that by finite elements, you will readily notice that all the sequence of problems have the same tangent stiffness matrix, so no need to update. Okay, you solve sequentially the problem for all the different orders. If on top of this asymptotic expansion you introduce the PGD, you obtain an expression in which the displacement is a power series of A, the arc length parameter, and also a separated representation in terms of physical coordinates S and load position S. Well, this works very well. Consider, for instance, the example I showed before, a cantilever beam, okay, nonlinear, new Hookean, hyperelastic, and you can see here the solutions for different orders of expansion. Order 1, this is the traditional linear elastic solution, a big gain in volume, no physical visual realism. Order 2, still a bad solution. Order 3, things are progressing. Order 4, why not? This is more or less an accurate solution. We can compare the solution with, here in blue, is a traditional finite element solution of the problem. You can see how from order 1, 2, 3, 4, you approach progressively the nonlinear behavior of the beam. You can do the same for the lever. We particularize, for instance, for any position S of the load, and for the nonlinear response of the lever, you can see that in this case, with an expansion of order P equal to 6, we obtain a very nice approximation to the solution, even far away where the finite element simulation broke by lacking convergence. Okay, just to show you how these functions x and y, depending on the physical coordinates x and the position of the load S, look like. Okay, this is the spatial modes for the first order, the spatial modes for the fourth order expansion, for the fourth order term, and the terms for the load. These are defined only, these are 2D. These are defined on the manifold of the surface of the lever only. Okay, for the first and the fourth order of expansion. Well, in practice, how does it work? You see here the haptic peripheral. You feel, you notice the force in your hand, and at the same time the lever is responding as expected in real time. No jumps are perceived, and the physical sensation is, believe me, very, very accurate. But so far, this is quasi-statics. Okay, maybe your question is how to manage to store in memory everything when you deal with dynamics, with initial and boundary value problems. Okay, this is also a challenge. When history plays a role, how can you store everything in memory? Well, let us consider the standard formulation for solid dynamics, initial and boundary value problem, the initial conditions on displacement and velocity. In this case, our idea was, of course, we work with waveform in a traditional way. This is just for the purpose of notation. The idea is to develop a vademecum, that is the solution of a parametric problem in which the parameters are precisely the initial values of the problem. Thus, the initial displacement and the initial velocity of the problem. So that we obtain a vademecum that is defined in the geometry of the solid, say the lever, for the initial time of the time increment of your simulation to the final time of your time increment, and also the possible interval of variation of the initial displacement and velocities, but once discretized, the displacement at time n and the displacement at time n-1. Okay, you consider a possible range of variation wide enough, and we compute this kind of vademecum. Okay, so we redefine the wake form of the problem so as to make it triply wake, in the sense that we integrate in omega and on the intervals of variation of initial conditions. Okay, so now the displacement field depends on the position, on the physical point, on time, and on the initial displacement and velocity. And the expression is the traditional separated form of the PGT method. V, as a function of t, play the role of the typical finite element time coefficients. This is not a function. We are not computing a space-time solution. These are coefficients rather than functions. The method works equally as in the previous case. You look for the new terms in the expansion, and what we finally obtain is a sort of black box. You feed the black box with the results of the previous time step, and this black box will give you, taking these results as parameters, will give you the displacement field at the end of the simulation. The problem here is that the space of initial conditions has potentially many degrees of freedom. Consider, for instance, the mesh of the lever with some 35,000 of nodes. Multiply them by 3 spatial degrees of freedom, and you obtain a lot of parameters, several hundred or of thousands of degrees of freedom. These are too much parameters even for PGT. So what we do is to project these results in a better parameterization of the space of initial condition. And this parameterization is obtained by means of PUD. We solve a sort of a group of full problems. We obtain relevant information for them, and we construct a basis with very few degrees of freedom, and these results are projected onto this basis and re-injected again in the black box. Okay, that's the policy. To see how it works, an elastic block on top of which we apply a step load. Okay, you see here the waves traveling all along the block. Well, we compute the solution by employing standard finite elements and by employing our reduced order method. The time step in this example coincides with that required by the haptic device to provide an accurate sensation. Here, the continuous line is the reference solution, and the dot red and blue lines are the solutions for points A and B, respectively. Here, the basis for the parameterization of the space of initial conditions contains only 3 degrees of freedom. And you see that the results look quite nice. If we increase a little bit the number of degrees of freedom of these bases, 8 bases for the space of initial conditions, you see that the results improve a lot. And you can employ here your favorite time integration. Okay. For instance, if we employ energy conserving algorithms, you will see in a moment that we obtain results for an integration time step of 0.001 between 0.0009 and 001. So nearly in the very accurately in the real-time limit, and using a standard laptop with MATLAB. No special requirements are needed. Okay. Well, as I mentioned before, if we employ an energy momentum conservative integration schemes, the results are almost exact for even for long times of integration. These are 10 seconds. Okay. Well, let's take a look to the results. Consider the palpation of the lever. We apply a load and then release. Okay. No damping is considered for the moment in order to test for the artificial numerical damping in the method. You will notice if you focus on the results here that the reference solution, which is the black line here, is progressively achieved by considering 1, 3, 7 modes of the basis. Okay, you see that with 7 modes, the blue line progressively approaches the reference solution. At a given level of accuracy, you won't be able to feel in your hands these very small vibrations, and at that level, you can truncate your basis. Just to show you how this works in practice, if you implement this in a web page, these algorithms, this is running in Safari, okay, you can play, you see the mouse, and you can play with the beam and see how it works. Every time I put the mouse on top of the beam, I apply a load, okay? And it works perfectly in real time. Even in this case, we are obtaining visual real time, but it is an implementation in a web page running JavaScript, okay? Well, just to finish some topics in which we are working at this moment. There are some remaining aspects of surgery that go beyond this kind of approaches that I mentioned before. One is that of contact. How can we simulate contact in this framework of storing in memory as much as possible? Okay, well, the method that we have implemented is a very simple method in which we consider the contact between two different solids. One of the solids, say omega-1, is equipped with a level set function containing a distant function. Okay? The other, say omega-2, is a point shell. That is, we consider a shell of marker points on the boundary of the solid. So each time these marker points go within the level set that accompanies the solid omega-1, the distance is computed, okay? And once one of these points in the shell crosses the 0 level of the level set, we have detected an interpenetration of both solids. In that case, just a penalty force is applied in order to separate these solids and to prevent interpenetration of both. Here you have the case of a beam penetrating, just the moment of penetrating on top of a rigid solid. Okay, you can notice here the level set field traveling with it is 3D. It's just a slide of the 3D level set traveling with the solid omega-1. Okay. This works very well even for very complex geometries. The classical benchmark of the Stanford Bunny. Here we consider that the two solids, one in red, one in blue, and they cross and they touch in the ears, provoking the displacement of the ears. You can see also the level set field accompanying those two solids. Again, an implementation in a haptic environment. You can see that we use a standard laptop, okay, And just by playing with a haptic device, you can manipulate the beams. And what is impressive is the sensation of the increase of the stiffness of the system once both beams get into contact. The other important aspect in the simulation of surgery is of course, cutting. How to store in memory every possible cut that a surgeon can make in an organ. You would say it's impossible. Well, I agree, it's almost impossible. But the approach that we follow is based on a combination of PGD and ECFM. We consider the displacement as a continuous part and a discontinuous one. Okay? The continuous one will be reproduced by PGD, and the discontinuous one will be reproduced by standard ECFM techniques. Okay? Once a cut has been produced, we project the results onto the PGD basis and the ECFM basis, say in a POD way. Okay. The other ingredient is not a standard ECFM technique, but the so-called crack node method developed by Ted Belisco, in which we consider only cracks that cross the nodes. Okay? We consider a discrete description of the cracks that nevertheless, for a dense enough mesh, provides very convincing results. An example, surgery for the correction of astigmatism. This type of surgery some years ago was made by acting on the cornea, by just cutting the cornea, by modifying the stiffness. The cornea is subject to internal pressure, so by cutting and changing the stiffness of the cornea, a modification of the shape of the cornea is achieved. Okay, so the idea is that this is the cornea, a very detailed view of the cornea. The idea is to be able to practice cuts in the cornea. Okay, consider for instance that we will pass a scalpel through points 1, 2, 3, 4, making a cut in this cornea. Well, this is, as I mentioned before, almost immediate. You can see how the cut progresses on top of the cornea. Well, in conclusion, we strongly believe that the use of computational vademecums has a potential tremendous impact in the community, not only as a help for daily engineering practice, but also for many aspects related to real-time simulation. And computational surgery is just an example. Imagine the potential of these techniques in the game industry, for games in which not only the results of your games are not just presented in your screen, but simulated, and with the possibility of having touch in your as a feedback response. Also in industry, for virtual prototyping. Why not in augmented learning? Why not including vademecums to help our students to learn strength of materials, for instance? Okay. What is important is that even for very complex, non-linear, state-of-the-art numerical simulations, we are able to achieve kilohertz feedback rates without any special hardware. Okay, thank you very much for your kind attention. Of course, please.
What control mechanism do you have to guarantee that your configurations in those direction and magnitude are represented during the evolution of the solution
you just take them as a parameter. Okay, the most general formulation includes not only the position of the, just a moment, not only the position of the load, not only the position of the load S as a parameter, but also the value of the three components of.
But they have to live in a. You have a basis in a certain space that translates into the reduced order model to the full order model.
Oh, you mean follower loads?
Yes, in everything you have to live in the same space. Otherwise, if I translate, let's say, in the haptic device, that such configuration is not allowed.
The case for the follower loads is somewhat a little bit more involved. You're right. You're right. In this case, it's a standard formulation, just where T, not only the position but the modulus and orientation of the load is the case of follower loads is still in progress.
Any more questions? Yes, please.
I would have a question. Thanks a lot for your very interesting talk. I would be interested in some of the implementation details. So we know a standard. Thanks a lot for the microphone. So we know a standard computer mouse has a delay of tenths of milliseconds. A standard computer monitor has a delay of at least 20 milliseconds. And everything you do on a standard PC is not really deterministic. So did you actually consider special input devices, special output devices, or a real-time operating system necessary to get that 1 millisecond feedback rate?
Well, it is important, the 1 millisecond feedback rate, it is important for the haptic device to avoid unphysical jumps in the response of the force, okay? This is related to the freehand oscillation frequency.
Yeah.
But it is not so important for visual perception. For visual perception, 1 millisecond is nothing. You will not perceive this delay, okay? So, in practice, many implementations use parallel computers for visual contact detection and for deformation computation. We use only one thread, one single core, and everything in a single thread, okay? And no delays have been perceived. It gives you a perfectly physical sensation.
Thank you very much.
Thank you.
Speaker again and move forward in the
Thank you so much.